All right. Today I'll be talking about memory leaks, especially two classes of memory leaks. That will be elements leaking and closure context being retained. I've thought about including more classes such as circular dependencies, but there is just no time for that. And I think circular dependencies, especially, they don't happen that often. So my name is Bartłomiej Dudzik. I'm a software developer at Main Matter. You can find me over on LinkedIn, and there is my GitHub. I usually use the same handle everywhere. So let's get started. This is sort of the outline, though those things have been changing quite a bit throughout the last couple of days. Every time I looked at the slides, I had a different concept going, and at least today I haven't been looking at this, so today it didn't change. Here is a small graph. I'm not sure if it shows the thing correctly, but this sort of illustrates the how technically, more or less, our applications look like. So we have the system, that will be the browser, which would be the root element of window and document. Then we have our application that lives under it. Application has services, routes. Routes usually have components, and they all produce some kind of HTML. Forgot to mention, the gray out route is the one that we are currently on. So how memory leaks happen. So we are on the user route, and when we switch to another route, what we want is just this one route producing HTML in the memory. It's not actually what happens. So there is a memory leak. So there is a couple of components leaking, and where are they held? Is it the system, or is application having a hold of them? Something has a reference to those, and garbage collector doesn't know what to do, because from its perspective, it's still reachable. Because garbage collector, the market sweep algorithm, what garbage collector in JavaScript does is, if it can't reach some kind of memory from one of the roots, the GC root would be the window, the application, whatever. If they are not reachable, then they are being removed from the memory. But if something still has access to them, then they won't be removed. And that's the principle of a memory leak happening. Here is a small example. It's very trivial, but this already can cause a lot of problems. So we have a classic situation of listener not being removed. So we attach an even listener to a component, and we pass to it a function that has a binding to that component. So the handle clicks context is the component, and that component is leaking. And when it's leaking, the HTML also won't be removed. And this is pretty much the same, but with an anonymous function instead, with a closure. This is all you need to do to cause a memory leak from a component. And the fix is pretty simple for these situations. You just need to remove the listener, right? Always remember that wherever you have add method, there should probably be remove method in the same context. That's probably a pretty good rule of thumb. And I would say that in principle, anything that any child of some parent, when it tries to reach to that parent, especially when it tries to handle it some kind of reference, it creates a situation where a memory leak might happen. So here we are basically passing this context to some higher level, that is the window, and that's the memory leak. So similar situation here, not listeners, but we have the service. The service takes some reference to the components. We are adding components to application service, and that also keeps a hold of the references, and they are not memory leaked. They are not GC'd. So again, the solution would be to remove it. Here is an interesting case as well. I took that from Jake Archibald. It was pretty good timing as well, because when I was preparing that talk, that blog post just was released. So here in the demo function, what's happening? We have a big array buffer. Then that demo produces two closures that are bound to the global disk. And what's interesting is that only innerfunc1 is using the big array buffer, and innerfunc2 doesn't. So the expectation, at least for us, what seems logical, is if we remove the reference to innerfunc1, if we remove the innerfunc1 from the global disk, then the big array buffer is going to be removed from the memory, but that's not what's happening. Actually, what the engine does is it creates a single context for this whole function body, and that single context object is being shared between these two functions. So unless both functions are removed from the global disk, it's not going to be the big array buffer is not going to be GC'd, and I will pop it right into my console as well, because we're going to be doing a little bit of live coding as well, which is not wise, but that's what's going to happen. I'll pop inspect. I'll go to the console. Great, it switched slides, but we'll see. I'm going to paste it in. Click enter. That should already allocate a bunch of stuff. We're going to grab a snapshot of that thing. And at least this situation, well, because it's hypothetical and the big array buffer is big because it's 100 megabytes, and we can pretty much see it from already from miles away, because there's a big 100 before it. So yeah, so let me find that real quick. So here we already have when we filter through the retain size, and when we filter through the retain side, the system context actually appears first as well, and we can inspect that system context for that function. And over in the retainers, we can see that this system context object that I was mentioning, that is created for that whole function body, is being used in two functions. So if and this is why even if we remove innerfunc from the global disk, it's still going to be, the big RFR is still going to be retained, because the innerfunc also uses that context. But yeah, don't worry about the context in stuff. I'll be explaining that in a moment, but I just wanted to visualize the context leaking for these two closures. Okay, so a big part of working out memory leaks in your applications would be preparing the environment. I have had too many situations where not using production environment tripped me over, because Ember has, Ember maybe especially has a lot of debug code, which is very useful for debugging development and everything. That's how we get pretty good messages. But when you're working out memory leaks, it's going to cause problems. So you want to use production environment. And when you're using production environment, then your code is going to be minimized and everything is going to be mangled up. So it will be difficult to inspect the snapshot. So the first thing to do is to prepare the environment, and to prepare it, you will need to instruct Cursor to preserve class names and function names, so they are clearly visible in the snapshot. Then, if you're supporting older browsers or many, yeah, if you're supporting older browsers, then at least for working out the leaks, you might want to specify only last couple browsers, so there's also less noise in the snapshots and generally less code. So here is pretty much a small summary of what I said, with addition of you shouldn't use browser extensions either, and ideally, and maybe just use incognito, because they usually by default don't have extensions in them, because extensions are also running on the same in the same context as the application, and they also, especially in case of something like Ember Inspector will also try to get a hold of the references of your components, and that's going to be creating a lot of false positives, and that's also something that tripped me over. So here would be the video of the AMP, but we'll be looking at that later. So yeah, when working with memory leaks, when you know about them and you want to find them quickly, here is a couple tricks. And that is, and the trick is leveraging the Q&A testing and just triggering. And here, for example, we are triggering route visits multiple times. Then we post test, and we can post test and grab a snapshot. But I know I'm slightly contradicting myself here, because I use production environment, and yes, you should use production environment. But if you want to do some quick checks, especially if in production there is a lot of steps to find out stuff out, then it's at least initially it's fine to use test environment, in my opinion. But in the end, it will need to be confirmed in the production, because the test environment has the debug code. Here is a similar case. With just generating tests, and these two differ in a way that when you're running, when you're repeating steps inside a test, then that test is going to be running the visits for that one application. So that one application is going to be growing, and that's. And this scenario is specifically for memory leaks that happen in the application itself, and they don't necessarily reach to the window or document object. And this trick, on the other hand, because when the test finishes and the application is being torn down, ideally everything is GC'd, but if it's not, then if you want to reproduce those situations, then you can just generate a bunch of tests that will leak the application itself, and yeah. Anyway, another trick would be to use for production environment. You want to use also define yourself a couple helpers. So we can do something like this, just execute some code in the console, and here we are paginating every 250 milliseconds in a loop, and over it, and that's also another way to blow up the memory, so it's easier to find this stuff out, but in the production environment. Here is a small plug. So a few years ago, Steve Szczecina created a Ember CLI memory leak detector. It's unusable currently for older version of Qt, and also because I wanted a couple of features of it, one more feature, I basically stole the code base and yeah. And released it, yeah, and released it, and here is how it works. So on the screenshot on the left side, well, maybe I'll use this thing. So here, for example, we are running a check that runs after the whole test suite. whether the test suite itself is leaking. So this scenario would indicate leaks that happen above the application level. And here is also a couple screenshots for how it will look in CI. And here is the code for it. So we import the function from the memory leak detector, run a very complex test script because we need to run the memory leak detector that is a node server, grab its PID, run the test itself, and wait for the outcome of the server. Because when that function finishes, it's going to close the server. The different kind of test would be checking directly while our application is running whether there's any instances of our component in the memory currently. So, for example, you could paginate a bunch of times. We are on the users route. We paginate a couple of times, and the expectation is that there is only 30 of those components in the memory currently, and we assert it. But if there is a memory leak, so yeah, here's a bit of code. So it doesn't really matter. But yeah, so we have added a feature that caused a memory leak, and now we have and the count of user list component isn't 30, but is 120 times, which is the initial load and 3 more iterations of pagination. And now it's going to be a little bit of the light coding I promised. So let's see. So we're gonna open the application. It's running currently in the in the production environment. We're gonna go to this awesome page. I wish I had the Pokédex that Chris made, but I don't. It's slightly worse, and here we will be looking for we'll try to estimate where the memory leak is actually happening. So I'll open the performance tab first, select for memory, and hit record. So now we are recording the performance, and we're gonna play with pagination a little bit. Go twice next, then GC. Remember to hit GC because it's not done automatically. Then maybe previous again, and make sure to click GC. And that gives us a pretty cool graph of what's happening in the memory. We're gonna select as well the heap, and nodes. So here is what's happening. So here is what it tells us. So maybe I'll use the pointer. Over here is our initial load. Here is the first pagination. Here's the second pagination. Here we hit the garbage collection. Then we do pagination again. Then we do pagination again, garbage collection, and ideally those lanes would stay the same, but it's not what's happening, and that indicates a memory leak. So even listeners are staying the same, and they are not necessarily indicative of a memory leak itself. I think it's better to use the nodes rather, and the JS heap size. So every time we paginate and hit GC, the heap is rising as well as the amount of nodes is rising, and that would mean that the memory leak is somewhere on the HTML producing side, and in our case that will be components, routes, or something like this. So now I'm gonna take a snapshot of the memory, and here is a couple of things we can check. So because we configured Terser, and we have class names to play with. We can search by components. We can see that there is too many of our, I can't actually see from here, but here is too many of user list components because we only expect 30. And if we don't necessarily have class names to play with, we can look for detached HTML. And detached HTML is an HTML that is not currently rendered in the DOM, but it's still used somewhere but the JavaScript side is still referencing to it. And when JavaScript has a reference to an element, but it's not rendered, then it's in the detached state. It might not necessarily always mean a memory leak, but if it blows up like this, then it probably is. So here it works as if we console log this element. We can inspect its properties and everything. And when we select an element, we can look at the retainers. And what does retainers say? So retainers say that this element that I just selected is a 28th element in an array, some kind of array, we don't know which one. It's a generic name for the whole array class. That array is lives as or is retained as elements in some other object. You can sort of read the retainers diagonally. So if you go from the array to the elements, it means that this array is somewhere is a property in some object, and that property is called elements. And we can sort of confirm that as well. So we can grab a variable. We can grab that linking object as a variable. And here we have this list. We can grab this object as another variable. And we can try to compare whether the reference to the temp2.elements equals temp1. And it's true. So that sort of confirms, that gives us a visualization of the relationships of these retainers. And another thing the retainers say is that this element is retained inside a did intersect modifier, and that did intersect modifier is this variable in a system context, and that would mean that the this is and that system context is also a context in some anonymous function. That's what the parentheses mean.
Yes.
So yeah, we can't really log the system context themselves, but we can, for example, log the function that has this did intersect modifier as context. And when we do that and click on the logged function, then we are redirected. If we have source code, we are redirected to the source method. I mean, we can get redirected to the source code of that thing. Yeah, and this basically goes on and on. We haven't really found a memory leak yet. This goes a bit deeper. So let's read that. So the did intersect modifier lives as this in a system context. That system context is a context in an anonymous function. That anonymous function is an enter property in an object. That object is being passed to a bunch of stuff. The grayed out parts, they come from the system. And this is, yeah, this, for example, and it's, And I still don't really understand those parts, but we can go a bit deeper. And finally, we arrived at the enter, that this object that has our leaking function goes into some kind of registry. That registry is also lives as a registry inside intersection observer admin, which is a context of a bound function. And so this is the difference here is this is a function that uses function.bind as a binding instead of using a closure. Then we have some V8 stuff that's engine listeners, and then it's just and this is basically some native platform objects. But what we are interested in is the registry registry here, because it's pointing us to some external code especially. So that would be the place to look at in this case. We can also look at it from the other side, and that is from the component. And this is pretty much the same as well. We can select that component and read it as the component is a context inside. Is bound for some function. That function is a property last value inside some reference impl, and that reference impl is we don't necessarily know what that is, but that's probably some Ember stuff. Then we have callback ref, and that callback ref would be is also colored in as purple, and that means it's a variable inside some other system context. That context is used in an anonymous function. That anonymous function is a onEnter property in did intersect modifier. So this basically points us as the did intersect modifier add-on.
Yeah.
And here is my, and that's how we would be looking for memory leaks, essentially. I think the biggest breakthrough for me, especially, was reading the retainers, that they sort of go diagonally, and the first thing, the very first thing means our selected object, and then as we traverse down, it's being passed down into some other properties, and yeah. But yeah, my favorite way to figure out a memory leak is just delete some code, and that would it's probably the most efficient. So here we have our route. Here is some pagination. Let's imagine that the user is using some data loading. So if you want to rule out some data loading issues, then you can just leave the bare minimum of the template. I'm going to remove the user list component. Let's see if that reloads. Oh yeah, it reloaded because there's nothing. So we can play a bit with the pagination again. Maybe it will be triggering some requests or not. We'll just jump straight to a snapshot. And if we look for any components or detached HTML, then there is pretty much almost none. This not necessarily might mean, because there is no big numbers of those things, it probably means that they are not necessarily a memory leak, so we can ignore those in this case. So that points us that the problem is probably with the user list component. And we can go a bit further, and we could just keep on deleting stuff as we go. And here is some code comment that I forgot to remove. But essentially, this is inspired by the fact that on the client project we had an issue with a leaking modifier, and that modifier was the in viewport. And the issue was with another library that they are using, which is since fixed. So if you are using any of did intersect on the in viewport, you might want to make sure that now I don't have it here, that the intersection observer admin package is one deeper. That the intersection observer admin package is at the version 0.3.4, and that way you should be memory leak free, at least in this scenario. So yeah, I think that's pretty much the end. I'm not sure. I think I'm pretty much on time. So the memory leak topic is pretty enigmatic. I certainly was panicking when I found my first one and the second one and the third one as well, because I don't know how to deal with them after this time. And each time was like 3 or 4 years away, and yeah, and that's how it goes. Nobody cares until they happen, and when they happen, in the worst scenario, and the worst scenario is when the customer reports that, and that was also what happened for our client. So here is a couple references that I used. So yeah.